So this is the second video on separation axioms. Already we have seen Hausdorff axiom. The other axioms are similar but stronger. As always, when we introduce new concepts, we shall examine relationship between these axioms and concept introduced earlier. Recall that T2 axiom, namely separate every two distinct points by open sets. Recall X is Hausdorff if for every two distinct points X not equal to Y in the space X, there exist disjoint open sets containing X and Y. Okay, so now we define regular spaces. So in this video, in this lecture we always consider the topological spaces are T1. Okay, so that is the singleton sets are closed in the space. Okay. So let us define regular spaces. Suppose X is T1. As I said, we will consider the spaces are T1. Okay. So suppose X is T1, then X is called regular if for every point X and closed subset C that is disjoint from X, that is X does not contain in C, there exist open sets U and V containing X and C and they are disjoint. That is for every closed set C and a point X which is not in C, there are disjoint open sets U and V containing X and C. Okay, so this is the definition of a regular space. So of course when C is singleton set, so when C is singleton set Y, so you can see there exists. So if a space is regular, then it is Hausdorff also. Okay, so in particular we consider C equal to a singleton set Y where X is not equal to Y. So here we have a remark. A regularity is topological property. That is, if F is a homeomorphism between two topological spaces F, X and Y, then X is regular if and only if Y is also regular, and it is product preserving property. Means if you have a collection of regular spaces, let's say X alpha belongs to some index set lambda, then the product space X equal to product X alpha runs in the index set lambda, and X is equipped with product topology, then it is also regular. Okay, so this is the definition, and we have two remarks here. Now so note that regular spaces are also, I mean, this axiom is also known as T3 axiom. So a topological space X is T3 space or satisfies T3 axiom if it is regular. Okay, so regular spaces are known as T3 spaces. Okay, so as I said, so here already we have seen that regularity is stronger than Hausdorff spaces. So X is regular, then X is Hausdorff also, but the converse is not true, and basically there are topological spaces which are Hausdorff but not regular. So here we we give an example of topological spaces, topological space that is uh, Hausdorff, but it is not regular. Okay. So the underlying set is consider, so the underlying set is x equal to R2, so R cross R. So this is so this is plain R2, but here we define some new topology on the set x equal to R2, and that is known as slit disk topology. Okay. So to define the topology, so consider P equal to x comma y, the set of all points x comma y, such that x is not equal to 0. That is P is equal to R2 minus y axis. Okay, and also we define L equal to 0 comma y belongs to R2. Okay, that is L is equal to y axis. Right? Now we define topology on the set x, where x equal to R cross R, that is equal to R2. Basically, we define topology on R2, that is called slit disk topology, by describing local bases for the points in X. Okay, so let Z be a point in R2. So you can see R2 equal to P union with L. Okay, so P is basically P is R2 minus y axis, and L equal to y axis. So R2 equal to disjoint union of P and L. Okay, P in disjoint union with L, that is equal to R2. So if you take a point Z from R2, so that is in either, so we have two cases, Z is either in P or Z in L. Okay, so in the first case, consider Z belongs to P. So we describe a local basis at the point Z belongs to P. So namely, it is the open disk in R2 centered at Z, and that forms a basis of neighborhoods at the point Z. Okay, and so this is usual. I mean, open sets in Euclidean topology also. But if Z belongs to L, then open neighborhoods of Z are given by following the set of the form Z union with D intersection with P, where D is open disk with centered at Z. Okay, with centered at Z. So note that D intersection with P equal to basically D set minus y axis. So we delete the points on so when those are on the y axis. Okay, and union with Z. So this is basically two half open disk union with Z. Okay, this is connected at Z. So these are open neighborhoods at the point Z. So basically, if you draw a picture, so you consider an open disk around Z, and remove all the points Z comma so 0 comma y, where y is not equal to Z. So you are deleting all the points from D whose coordinates are 0 comma y, where y is not equal to z. Okay, so this is these are the open neighborhoods of z. So this so now so if you denote the set of open neighborhoods or local basis at z by bz, so bz is suppose bz is local basis at the point z, then the then the basis b is equal to union of bz, where z belongs to R2. Okay, this basis defines a topology on R2, and that is called slit disk topology. And of course it is Hausdorff, because if you take any 2 points, so if you take any 2 points Z1 and Z2 from R2, then there are open disk which are disjoint. So that open disk disjoint open disk will provide you open neighborhoods of Z1 and Z2 in the slit disk topology. Those are disjoint. Okay, so observe that x is Hausdorff, that is T2, but x is not regular. Okay, so here we have arguments where why x is not regular. For example, if you take a point 0 comma 0, that is that we denote by x. Suppose x equal to the point 0 comma 0 in x, and now we consider closed subset of x as L minus singleton set 0 comma 0. So this is closed subset of x. Why this is closed subset of x? Because see, L is closed in x. Okay, L is closed in x because complement of y-axis, that is open in the slit disk topology on R2, that's basically equal to x. Okay, so L is closed, and the subspace topology on L, that is discrete. Okay, that is discrete. Therefore L minus 0 comma 0 the point x, this is closed. Now now consider c equal to L minus 0 comma 0 and x equal to the points 0 comma 0, that is origin. Okay, so you see c is closed set in slit disk topology, and x is a point that is not in C. Now if u and v are open neighborhoods of the closed set C and x, then they never disjoint. Okay, and therefore x is not regular. So there are no disjoint open sets. Those u and v, those separate the point x from the closed set C. So this implies x is not regular. So here so we have constructed example, that is topology on R2, that is called slit disk topology on R2. That is Hausdorff, but not regular. Okay, so for more examples we have now for more examples of for example more examples we have the following lemma that says that subspaces of regular space, the subspaces of a regular space are regular. Okay, and the proof of this lemma is straightforward, so I am not going into the proof. Okay, so here now we prove characterization. So we characterize basically here we characterize regular spaces, that is if and only if condition when a space X is regular. So as I said here, so always we in this video, topological spaces are T1, that is one point sets are closed. So consider X topological T1 space, that is one point sets are closed in the topological space X. Okay, so then X is regular if and only if for every given X, little x point, that is a point in the topological space X, and open set U in X containing X. So there exists some open set V in X containing this little x, such that V closure is contained in U. Okay, so this is the characterization of regular spaces. So let us understand the statement of the theorem. So basically the statement says that, so already we have considered X is T1 space, then X is regular if and only if for every point X and open neighborhood of X, that is U, then there exists some another open neighborhood of X that is denoted by V, such that V closure contained in U. Okay, let us prove this theory. First we prove the forward part. Basically we assume that X is regular, and then we have to show that for every given X in the space big X and open neighborhood U of X, there exists another open neighborhood V of X, such that V closure contained in U. So our assumptions are X is regular. So our assumptions are X is regular and X is a point, little x is a point in the space X, and given an open neighborhood U of X in the topological space X. Okay, so these are the assumptions. Suppose X is regular and little x is a point in the topological space X, and third assumption is X is contained in some open set U in that space X. So what to show? We have to show that there exists another open neighborhood V. We have to show that there exists another open neighborhood V of X in the topological space X, such that V closure contained in U. Okay. Well, now consider the set B, which is equal to U complement. So already we have, so this is U, this is open subset of X, so U complement, and this is closed subset of X. So what is U complement? U complement is equal to X minus U, and this is closed subset in the topological space X. Okay, so consider B equal to U complement, that is closed in X. Now you see X belongs to U. Okay, so X belongs to U, so X is not in B. Okay, so by regularity condition, there are disjoint open neighborhoods of X and B. Suppose, so regularity condition implies that there exist UB and UX open sets in X, such that B contained in UB and X contained in UX, and they are disjoint. UB intersection with UX equal to empty set. Okay, so basically UB and UX, they are disjoint open neighborhoods of b and x respectively. Okay, and from this condition we have ux closure is disjoint from b. Why? Because if y is in b, y is a point in b, then the singleton set y is contained in b, because this singleton set is a subset of b and b is subset of ub. So singleton set y is subset of ub, so ub is an open neighborhood of y because ub is open containing this point y. So ub, this is an open neighborhood of y, and such that ub intersection with ux equal to empty set. This implies y is not in the closure. Okay, so this is not in the closure of ux. Therefore we have ux closure intersection with b equal to empty set. So basically this conclusion you can get from one line. From here you see ub intersection with ux, this is equal to empty set, and ux, so ux contained in ub complement, and ub complement, that is closed subset of x containing ux. So the smallest closed subset containing ux, that is closure of ux, that is contained in ub complement. Therefore ub intersection with ux closure, that is equal to empty set. Okay, well, so anyway we get ux closure intersection with b, this is equal to empty set. This implies ux closure contained in b complement. And what is b complement? B complement is so b complement is u, because b is equal to u complement, so b complement is equal to u. Therefore we have ux closure that contained in u. So basically here, so ux closure contained in u. Now we take v equal to ux, that is another open subset of so another open neighborhood of the point little x, such that v closure, that is v equal to ux, so v closure equal to ux closure that contained in u. Okay, so this is what we wanted to prove. So conversely, now we prove the converse part. So what is the converse? Let us go to the statement of the theorem. So x is t1, and so here we have the condition. So this is our assumption for every point x contained in so every point x belongs to the space x, and every open neighborhood u of x, there exists some another open subset of x containing x, such that v closure contained in u. So this is our assumption. So we have to prove that x is regular. Okay, so this is our assumption to prove x is regular. So what to prove? So basically for regularity, you have to show that for every point, so for every point x and closed subset c in x, such that x is not in the closed sets. So here we have denoted by b, in the closed subset we have denoted by b. So basically suppose x belongs to the topological space X, and little x, this is not in B, where B is closed subset of X. So we have to show that there are open sets in the topological space X containing this little x and B, and these open sets are disjoint. Okay, so basically we have to separate this point and B by open subsets in disjoint open subsets in X. Now consider U equal to B complement, so that is equal to X minus B. So U equal to B complement, which is equal to X minus B. So B is closed, that means B complement, that is open. So X minus B, this is open. Therefore U is open, and of course X is not in B, so X is in B complement. So U, this is open subset of X containing X, that is U is open neighborhood of X. By assumption, there exists some another open neighborhood of X such that is V. There exists some another open neighborhood V of X such that V closure contained in U. Okay, so V closure contained in U. Now we consider W equal to V closure complement. V closure, this is closed, so V closure complement, that is equal to X minus closure of V, this is open. So W is open. Okay, so W is open, and V closure contained in U. So V closure contained in U. So X minus U contained in X minus U contained in X minus V closure. So X minus U contained in X minus V closures, that is X minus U contained in W, and therefore X minus U, that is equal to B. So X minus U contained in W, so B contained in W, so B contained in W. Okay, so and W is open in X. Okay, now we consider V and W. These are disjoint open. These are disjoint open sets in X. Okay, by construction, V and W, these are disjoint open sets in X, because see V is open, contained in so V is open, and so here we get by assumption V is open in X, and W is X minus V closure. So this is disjoint from V. Okay, so V and W, they are disjoint open sets in X such that X is in V and B is subset of W. So B is subset of W. So V and W, they are disjoint open sets in X such that X in V and B is in W. So this concludes that X is regular. Okay, this is the characterization theory. This completes the proof of characterization theory. Okay. Now we define normal topological spaces. As I said, now we consider topological space X T1 space. Okay, let X be T1 space, then X is called normal, or this is T4, X is T4. If for every pair A and B of disjoint closed subsets of X, there are disjoint open subsets U and V in X such that A contained in U and B contained in V. That is, X is called normal if one can separate every pair of disjoint closed subsets of X by disjoint open sets in X. Okay, that is, if A and B are disjoint closed subsets of X, then there exist disjoint open subsets U and V containing A and B. Okay, now we have remarks here. Regular spaces are Hausdorff. So already we have defined regular spaces are Hausdorff. So after the definition, so I have said that if you take C equal to singleton set, then in this particular case, this coincide with the condition of Hausdorff spaces. So irregular spaces are Hausdorff spaces. Okay, so X is regular means X is Hausdorff. So the X is regular implies X is Hausdorff. Now, similarly, X is normal implies X is regular. So basically, in this case, you can take one of A among A and B. You can take suppose A is singleton set X. Okay, so for so X is normal. So in the particular case, when A is singleton set, that coincide with the definition of regular space. Okay, so every normal space is regular also. So normality is stronger than regularity. So T4 is stronger than T3. So I would like to give an exercise. Find some normal. Some regular spaces. That is, find some regular space that is not normal. Okay, that is an exercise. So here again we have characterization theory for T4 or normal spaces. It says that X is normal if and only if for every X is normal if and only if for every closed subset A in X and U open subset of X containing A, that is A closed in X and U open in X with A contained in U, then there exists some another open set V containing A, that is A contained in V, such that V closure contained in U. So basically first of all, so as I said, we consider X is T1 space, so every singleton set is closed. So this is our implicit assumption. Now X is normal if and only if for every closed subset A and open neighborhood U of A, then there exists another open neighborhood V such that V closure contained in U. Okay, fine. So basically this statement coincides with the characterization theorem of regular spaces. Namely, we have to replace this single point X by closed set A. Okay, so closed set A. So here and the proof is also basically similar. So basically we replace the single point X by closed set A. Okay, so the proof is exactly same. So still we go through the proof of this characterization theorem. Now so for the forward part, our assumption is following. So first of all, X is normal and A is some closed subset of X, and U is some open neighborhood of A. Okay, that is, suppose X is normal, A is closed subset of X, and A contained in U, and U is open in X. So what to show? We have to show that there exists some open subset V containing A such that V closure contained in U. Well, so now, as before we consider B equal to U complement. B equal to U complement, that is equal to X minus the set U, and U is open in X, so X minus U, that is closed in X. Okay, so B is closed in X, and already we have A closed in X, and A, B, they are disjoint. A and B, they are disjoint. So by normality condition, there exist open neighborhoods, disjoint open neighborhoods UA and UB of A of the closed sets A and B respectively. That is, there exist UA, UB open subsets in X such that this is open neighborhood of B, that is B contained in UB, and A contained in UA is open neighborhood of A, so A contained in UA, and they are disjoint. That means UA intersection with UB equal to empty set. Okay, fine. So from normality condition we have this. Now as before, we have UA, okay, UA closure that is disjoint from B. So UA closure disjoint from B. So basically here we have in the similar argument, if Y is in B, then singleton set, so that is contained in UB. Okay, because UB contains B and Y is in B, so Y is in UB also, and yes, therefore UB is open. UB is an open neighborhood of Y that is disjoint from A, that is UB intersection with UA equal to empty set. Okay, this implies Y is not in the closure of UA, that is UA closure intersection with B equal to empty set. Fine. And now this implies UA closure, this is contained in B complement. Okay, so UA closure intersection with B is empty set means UA closure contained in B complement, and B complement exactly equal to U. Therefore what we have, UA closure contained in U. Now you consider V equal to UA. Okay, then V equal to UA, that is open neighborhood of A and closure of that contained in U. This is what we wanted to prove. So for the converse part, so let us go to the statement of the theorem. So what is the converse part? The converse part is following. For given, this is our assumption for given closed set A in X and open neighborhood U of A, there exists another open neighborhood V of A such that V closure contained in U. So we have to prove that X is normal. Okay, so basically we have to prove that for A and B disjoint closed subsets of X there are open neighborhoods u and v. There are disjoint open neighborhoods u and v containing a and b. So that is, suppose a is closed in X and B is also closed in X, and they are disjoint, A intersection B equal to empty set. Okay. So now we consider U equal to X minus B. Okay, U equal to X minus B, and so we have considered B is closed in X, so X minus B, that is equal to U. U is open, so U is open, and A intersection B equal to empty set means A contained in B complement, and that is equal to U, so A contained in U. So what we have, A subset of U, and U is open in X. So by our assumption, there exists some V, open subset of X, okay, containing A subset of V, and closure contained in U, V closure contained in U. Okay, so now consider W equal to V closure complement, and that is equal to X minus V closure by definition. Now, as before, we see that B is contained in W, and W is of course open because this is closure of this is complement of closure, V closure, so W is open. Okay. So B contained in W, and W is open in X, and as before, one can see that V and W, they are disjoint open sets in X such that A contained in V we got here, so A contained in V and B contained in W. So this is the summary. The V and W, they are disjoint open sets in X such that A is contained in V and B contained in W. Okay, so therefore, so we can separate disjoint closed sets by disjoint open sets in the space X. Therefore, this means we conclude that X is normal. So this is it. So thank you.